Good afternoon. The objective of the study I'll be presenting today is to assess the reliability of pressure data as a leak diagnostic. And we were interested in pressure because pressure signals will arrive faster than other physical indications such as geochemical changes in the shallow groundwater. And hopefully a faster signal will allow for a timely leak diagnosis and then more effective mitigation action. And for this study, we're going to borrow a lot of the model parameters from a previous study that was in the NRAP program, which the previous speaker introduced briefly. And so we're going to borrow the leakage rates that were generated and also the aquifer heterogeneity parameters. And so these leakage rates were generated by separate reservoir and wellbore models. And the aquifer that was previously studied was based on the High Plains Aquifer in Kansas, and they were looking more at geochemical changes, whereas we're going to look at pressure. And so more details and background can be found in these two papers by Carroll et al. And so we'll use these already defined leakage rates as a CO2 and brine source at the bottom of our aquifer model. And again, the objective is to evaluate the efficacy of above zone pressure monitoring as a leak diagnosis. And specifically, we want to determine how frequently each of these four situations might occur. So given that some monitoring well observes a pressure signal, does that coincide with the leak or a non-leak? And so we can call these our true positive and our false positives. And then conversely, if we're not observing a pressure signal, how often does that actually coincide with the leak and a non-leak? So then we have our false negatives and true negatives. And since I'm using synthetic data, we have a suite of simulations so we can quantify the probability of experiencing a true positive or a false positive versus the true and true and false negatives. And so these probabilities are useful because you can use them in a value of information technique. And this is one of our goals in this larger term goal in this project, but I won't be going into the value of information calculation. But what that does is allow us to look at how often an information source will be successful at actually telling us what's going on in the subsurface. So you can think of these true positives and true negatives as a success, that this pressure data is telling us actually what's going on in the subsurface. And so many things will influence whether or not pressure data will be giving us the right message about if a CO2 or brine leakage is occurring. And for this study, we're considering these three parameters where we're going to vary the distance between the source leak and the monitoring well. We're also going to vary the different leakage rates of CO2 and brine. And then lastly, we'll vary different heterogeneity parameters of the aquifer. And so by varying these different parameters, we hope to be addressing these two fundamental questions. How close do we need to be to avoid false negatives? And temporally, what timescales does pressure provide a reliable leak diagnosis? So to get at that first spatial question, we're going to assume that the monitoring well could be anywhere within the simulation grid. And so our aquifer is 1 kilometer by 1 kilometer by 240 meters thick. And so given that we have a fixed leakage location shown with this star, this is a distribution of the possible observation distances we might have. So most of the monitoring wells would be 200 to 600 meters away from the actual leak. So the rest of the sampling and simulation workflow looks like this, where we're concurrently varying the heterogeneity parameters and the leakage rates. And so we'll generate 500 subsurface models where we're changing the horizontal and vertical correlation lengths and the different proportions of the facies. Here's just one example of a aquifer model where we have two different vertical slices. So you see that the facies are allowed to extend throughout the model. And then we borrow those leakage rates from the previous work. So we have 500 different leakage rates where I'm showing the cumulative CO2 and brine here. And it's important to note that since we were considering the short-term pressure data as a short-term diagnostic, we are only simulating 5 years, but these leakage rates are coming from simulations where the ramp-up time of leakage was 50 years, so we're not really accessing all of the possible magnitudes of leakage. Next, we combine those two to actually simulate the leaking well at the bottom of the groundwater aquifer, and then take all of those results and calculate what is the pressure change over time from this leak. And so specifically, I calculate the change in pressure in PSI for all time steps, for all grid locations, and for all 412 simulations that were successfully completed. So with all of these different observations, then we have a bunch of statistics where we can actually determine how often any 4 of these combinations are going to occur. But before we do that, we need to define what is a signal and what is a leak. And to do that, we looked at what is the actual detection threshold for a pressure transducer in a shallow aquifer. And so we define the leak according to what is detectable. And so an optimistic range of that typical accuracy of a pressure transducer is given as 0.1 to 0.3 psi. So we say if there's an absolute change of 0.3 psi at the location of the leaky well, we're going to call that a leak at that time for that simulation. And so that will help us define when our true and false positives and negatives might occur. So given this definition, if we look at all of our simulations, we can see how the fraction of these simulations, what fraction of these simulations are a leak at what time. And so this is showing the fraction here and over time for the 5-year simulations. So we see a majority of the simulations yield a detectable pressure signal at the leak location after 500 days. So we've covered what is a leak. Now let's look at what the signal is. So what would the pressure change be away from the leak location? So I'm going to show 7 different time steps of the pressure plume moving out. And the difference here is that I'll be showing the relative pressure change, so how that pressure is changing from its neighboring time step, whereas I'll define the signal and the leak as the absolute, so the change from time 0. But even given that, we'll see that most of the colors are in this blue range. So the pressure signal that's going to traverse the entire simulation grid is an order of magnitude smaller than our detecting limits. So here we are 29 days after the leak has started, and you'll see these nice smoke rings moving away from the leakage location. So 30 days, 35, 45, and so on to 75. And so if we then look at what is the maximum pressure disturbance or signal for all of our simulations over this 5-year time period, we see that we have really small pressure signals. So the majority of them are 10 meters or less away from the actual simulation or the actual leakage location. And so here it is just plotting how far away the pressure signal reaches in linear scale and then on semi-log scale below. So now finally we can calculate those 4 possible situations where we have true positive, false positive, etc. And here first showing again with the true positive and false positive. So positive means we're actually seeing a signal that's that's within or greater than our detection limit. And so what this is saying is if you're actually seeing a signal anywhere within our simulation grid, then you're sure there is a leak. So there's no, there were no instances of a false positive. And of course, this is a result of being a synthetic study. If you're actually in the field, there's definitely a possibility that you'll have some kind of interference or noise from nearby pumping that could possibly give you a a false positive, where you see a signal and there's actually not a leak. However, if we look at the negative, so we're a non-detect, so we're not seeing a pressure change greater than 0.3 psi, there is uncertainty. So here we're seeing, at the early days, the true negatives, so we're not seeing a pressure signal. That actually is more likely the case that there has not been a leak yet. However, as we go past around 300 days, now the false negatives are dominating our suite of simulations. And this curve here, of course, mimics the curve of how many of these simulations actually are classified as a leak. So that makes sense. And again, the statistics behind this are very much controlled by the distribution of our observation distances, which, so if we consider that that we're pretty sure that we're within 20 meters of the leakage location, we can then throw out all the observations that are greater than 20 meters away and just focus on any monitoring well that might be 20 meters away. So we recalculate basically our false negative and our probability of false negatives and true negatives for just observation distances within 20 meters, and we see that it does change our probabilities of having a false negative. So I'll switch back and forth a little bit. Oops. So here we see a slight drop. Now, if we focus in on the first 500 days, what this means is that the false negatives will dominate after 450 days if we're closer to the leak than instead of 300 days. So in summary, some of our observations, again, the objective was to assess pressure signal as a monitoring method for early leak detection. And we used CO2 and Brine leakage rates from a previous study for a longer term leakage rate scenario. And so here we're using just the ramp up stage of injection. And we see that false negatives are dominating, and that's again because our simulations are dominated by very small pressure signals. And so the current and future work is to run our simulations longer and see when pressure becomes a reliable method for detection, and to add back in geochemical reactions and use the value of information metric to compare the two monitoring techniques. Thanks. I went over.
We have time maybe for a quick question.
I just had, you were mixing both the CO2 and brine leakage. Did you also vary for the CO2 simulations, like multi-fluid flow properties, like relative permeability or capillary pressure effects?
There was no capillary effect in our simulations, and relative, well, it's a multi-phase simulator, so that's definitely included, but no capillary effects are in our simulation. But the CO2 and brine are leaking together simultaneously, yeah.
And your realizations were just varying permeability and porosity?
They're changing the correlation link, so how the continuity of the sand and clay facies and the actual percentage of the two, but the porosity and permeability are fixed for each facies.